Hey everybody, here we are back in the friendly confines of our chemistry lectures. So we're on episode number 6. We're working our way through acids and bases for the Chemistry 12, specifically to the BC curriculum. So today's class is kind of moving on from where we were last class. So last class we were talking about what was the difference between a strong and a weak acid or base, and then we kind of progressed into strong acids. How do you figure out the pH of a strong acid solution? And the concept being that a strong ionizes 100%, and so whatever the concentration of the strong acid was, it goes 100% into hydronium. That's your hydronium concentration. You negative log that value, and you get the pH. So today, as promised, we're going to go into weak acids. Now, there's several different pathways you can take in terms of the calculations of this. So today's class is going to be very specific to just one type of problem. How do you figure out the hydronium in a weak acid solution? And also get the pH from it. Once you have the hydronium, negative log it, you get a pH. So essentially that's what we're doing, finding out the pH of a weak acid solution. There are a lot of other calculations that we can do with weak acid solutions as well, which will be in the next class, as you can see. And so there's kind of two things that we're doing today. Number one, I'm going to show you a weak acid equilibrium and what a K expression for that weak acid equilibrium looks like. And then also introduce you to the Ka table, which if you're doing Chemistry 12, you will have some way of looking up the Ka values for the different acids, weak acids that you're going to be using. Whether it's an online resource that your teacher asks you to go to, or it's in the back of a textbook, or if it's just like a paper data booklet that you've got. I know in my classes I'm using the provincial exam data booklet from 10 years ago, I guess. And so in that data booklet on page 6, there's a table that says relative strengths of Bronsted-Lowry acids. So we use that as a resource for our values of Ka, which are equilibrium constants for a whole bunch of different weak acids. So I'll kind of introduce you into that, and then I'll go into an actual calculation that involves a weak acid. Fairly straightforward one. The calculation itself has kind of some intricate little pieces to it, a couple of new things to you for you to kind of dig into a little bit, which you haven't probably done before unless your teacher went into really kind of deep understanding and calculations involved with common ion and solubility. So we'll get into that as well. So the calculation will be a little bit longer. Now I need both boards today because these calculations don't fit on one board. They're long and a little bit more algebraically inclined. So we'll get into that. I'm going to erase the right-hand board over there, and then we'll get going here. Okay, so ignore what's kind of behind me here on this other board just for a minute. I did that in preparation because it was going to be a lot of writing. So the very first thing is just in general, what do weak acids do, and what equilibrium do they form, and what is the equilibrium expression for them. So if you recall, I use a very generic, and oftentimes people do, they'll use HA or HX as a generic formula for an acid. Meaning the A or the X being the anion that's associated with the acid, its conjugate base, and then with the H stuck onto it, kind of indicating that it's an acid. So I'm going to use HA, which is a pretty typical one. A being helpful because there's no such thing on the periodic table as A, so you can't mix it up for something that's actual real. So HA. If it's an acid, the H is the hydrogen is covalently bonded to whatever A is. So you take this molecule, this group of molecules that you've got, you throw it into water. First thing they do, as all acids do, is they'll form a molecular solution because it's got a covalent molecule. So the HA, the first thing it does is it dissolves into the water. It becomes aqueous. Once it is aqueous and it's kind of free from all the other molecules, likely you put it in there as a solid crystal. So it dissolves, it kind of starts floating around freely as an HA, bumps into water molecules. And the water molecules are liquid. Now, the arrow that I'm about to draw is dependent on whether that acid was strong or weak. The strong ones, they ionize 100%, and therefore I would use a one-directional arrow. I'd draw it left to right, one arrow. I'd even write 100% above it to indicate that that's what that arrow meant. Now this is we're talking about weak acids, which means that they don't really get rid of H's super easily. So what happens is an HA might bump into a water molecule, might go this way and form hydronium. And whatever the anion is, but because it's a weak acid, the H can go back onto the A- quite easily. Strong acids, it's kind of the opposite, where once the A- gets rid of the H, it's really hard, if not impossible, to put it back on there. So HA gives up an H, goes over, forms hydronium, forms A-, but it can turn around and go back the other way. That's why you'll see when you're talking about a weak acid equilibrium, you'll actually see the equilibrium arrow kind of being an indication that you're talking about a weak substance. Okay? So, having said that, there's your generic weak acid equilibrium. This, of course, if you're told a very specific acid, like if you're told you have dihydrogen phosphate, and it's a weak acid, well then you wouldn't put HA, you would put the actual formula for dihydrogen phosphate. You put it in there and you'd write your Bronsted-Lowry equation, and H comes off of dihydrogen phosphate onto water, and it would form your hydronium and your conjugate base. But that's the generic thing. The equilibrium expression for that, because the water is a liquid, you don't include liquids in your equilibrium expression. So the equilibrium expression, okay, will be the concentration of the products over the concentration of the reactants. So the products are the hydronium to the power of 1, because that is a coefficient of 1, times the concentration of the A-, the conjugate base, to the power of 1, because it has a coefficient of 1. So there's your products, over the concentration of the acid. Now remember, these are concentrations at equilibrium. So once you throw the HA into water, it does its thing and it gets to equilibrium. So all of that reaction kinetic stuff and the equilibrium stuff that you talked about way earlier in the year. So once it reaches equilibrium, and concentrations, they're not equal to each other, but once concentrations remain constant, hydronium times the A- divided by whatever the HA stopped at, that's going to be your equilibrium constant. And it's a constant, which means that if you're at the same temperature, if you're at 25 degrees, and you know that constant, it can be used anytime you've got water at 25 degrees and you've taken this acid and you've dissolved it, it will come to the same ratio of products over reactants no matter where you are. So as long as the conditions are the same, you can be sitting here in North Vancouver, or you could be in Orlando, Florida, or you could be in, I don't know, you can be in Cairo, Egypt. It doesn't matter where you are. 25 degrees Celsius water with this acid, it's going to come to the same ratio no matter what. Now, because this is specifically for a weak acid, again, it's like KSP was and KW was. This is a very specific equilibrium, and it's one it's a commonly used one, right? So this is of an acid, and so it's called the Ka. And so weak acids have a Ka, and so you might say, okay, so this acid's Ka expression is, and that would be the generic form of a weak acid equilibrium expression. Now, obviously, if you're going to do any calculations associated with it in chemistry, these are this is like one of our formulas that we have to use. You have to know how to do calculations at equilibrium, and you need to know the formula, like you do in anything. If you're in physics, you need the formula to be able to do the calculation. Chemistry, same thing. This is your formula when you're talking about equilibrium calculations. So we need to know how to do that first, and it's the same. Every single weak acid you have, it's going to be hydronium conjugate base over the acid. That's what it is every single time. You cannot come up with an exception. It's going to be that same way every single time. Now, those Ka values. Obviously, if you're going to do a calculation, you need to know different parts of this. Now, these parts over here, right on the right-hand side, the actual concentrations, we are going to be using, like you did in the equilibrium unit, we're going to be using, I call them IRE tables. Many teachers and many professors will call them ICE. They're the same thing. It doesn't really matter. I stands for initial. The R for me stands for reaction. C for other people stands for change. And then E stands for equilibrium. So those values over there and on that K expression are the equilibrium values. So you use that chart to kind of figure out the chronology of events that got you to equilibrium, which we're going to do. And then they fit on that side. So you're getting those three pieces of the equation from an IRE table. The Ka itself is, if it's a known acid, it's going to be on the Ka table, or you're going to be given it one way, shape, or form. You're not expected to know Kas off the top of your head. Some of them you're going to use so often that you're just going to know it, like it's going to stick in your head, and you've used it 24 times in your course, in your homework, and on quizzes and on everything else, that it's going to happen. It's just going to stick in your brain. So the Ka table becomes a very important piece of equipment for you. Call it, it's a resource, but you got to have your Ka table. If you don't have a Ka table, you're going to kind of be lost. So the Ka table that I use in my class is in the data booklet for Chemistry 12 that's been used in the province for the provincial exams. We don't have provincial exams anymore, but it's a very useful, helpful table. It follows the curriculum. It has on it what you need to have on it. And so you turn to page 6 and it gives you that table right there. And you can see that there's obviously multiple rows on this table. All of those things down this side down here are all different acids. So there's obviously lots of different acids that are on here. The 6 up at the top right here in the shaded region, those were the strong ones. And so they don't even form an equilibrium. So they go 100% to the product. So you don't need a K expression. You don't need any of this stuff for strong acids. You go ahead and you do the calculation based on 100% one-to-one stoichiometry. We've already done that, and that was last class. For the ones that are below, though, the ones that are in the white right here, so those are guys that ionize less than 100%. So they form an equilibrium. And it's the fact that they form an equilibrium is kind of why they have less than 100%, because the reverse reaction is actually significant enough that it doesn't allow the acid to move in the forward direction and unload a proton onto water 100% of the time before the thing turns around and goes back the other way. Now, if you have one of these things with you, you can kind of see it's organized in a very important kind of manner, and you can see there's an arrow on either side. So let's start with the one on the left-hand side of this table, and I'll move it a little bit closer here. So the arrow talks about the strength of the acid. So as it goes up, the strength of the acid goes up. The strength of the acid meaning how well it ionizes in water. So moving up, and the top ones are obviously the gray ones that are 100%. So the ones just below, it doesn't mean they're just below 100%. It just means they're weaker than the ones that do go 100%. And as you go down and down and down and down, they get worse and worse and worse and worse and worse at unloading an H onto water molecules. You get down to this bottom gray section right here, there's these two down here. They are acids that don't do it at all. They are 0% acids. Now you might say, well, why are they on the table if they're 0% acids? That means they're not acids. They don't even do it. So Why put them on the table? Well, the table, as you're going to learn, has dual purpose, and it has dual purpose by looking at the other side over here. And the arrow on the other side talks about the strength of the bases. This table actually is a table not only of Kas and of acids, it's actually also a table of the bases. And so we'll get to that kind of intricacy when we get to the bases, but the far right-hand side over here acts as a resource for the bases as well. We'll get to that one. Let's not panic about it right now. So the table that I've got right here, it gives you a whole bunch of acids kind of listed in order. Now what I've done behind me here is I've done on this side of the board over here, I've put, how many did I put? 1, 2, 3, 4, 5. So I put 5 on this board that were on that chart. Okay, so I took them straight off the Ka table. So a couple of things about the Ka table before we move into the actual calculation. It gives you relative strengths. Okay, so it puts them in order from like the strongest acid at the top down to the worst acid down at the bottom, and everything kind of in between, all in its specific spot. And you'll see, like if you look at the numbers for Kas, they get progressively smaller and smaller and smaller and smaller as you go. So I've put 5 representative examples up here on the board. So the first one that I put up here is perchloric acid, and you'll find perchloric on any Ka table out there in the world. Doesn't matter if you find it online, you're using the one from our provincial exam, or you're in Alberta and you're using a completely different one. It'll have perchloric on it, and it might be in a slightly different format of how they're writing it down, but it'll be there and it'll have some equation, and it will probably say something to the effect of Ka is very large, or it might use the actual infinity symbol, or it might actually give a number. I mean, who knows? It might give you something like 10 million or something like that. The concept being that it has a single arrow. Okay, and so that single arrow right there is indicative of the fact that perchloric goes 100%. And that's why it's got a very large Ka. They didn't even put a number there. Why? Because they don't even want you to bother calculating it. You can't calculate with the words very large. So it just means, hey, do you remember this is 100% and you're supposed to be taking the concentration of the acid equals the hydronium? The table's trying to tell you that. Like, don't do math, you're supposed to know this type of thing. Okay, so that's perchloric. You go down and you find hydrofluoric. Now, you go down and something that you've noticed that I haven't put up here yet is that the arrow has changed. So the arrow will now have both ways. So that indicates that, okay, so this guy significantly, HF, goes both ways, right? The perchloric one only went one way. So if you've got perchloric acid, it's going to the right-hand side and only the right-hand side. The hydrofluoric is not. Okay? It gives you the number, whatever that numerical value is. It's small. I mean, 3.5 times 10 to the negative 4, that's small. And as you've learned, that between 1 and 0, if you've got a number less than 1, obviously positive, less than 1 is an equilibrium constant. That means that your reactants are favored. And so 10 to the negative 4, the reactants are favored. Products over reactants, yeah, the reactants are favored. As you go down, next one I put is ethanoic/acetic. I'll get to that in just a sec. Again, double arrow. A little bit lower of a Ka, further down on the table, smaller Ka. Therefore, it favors reactants even more. Okay, so ethanoic acid produces less product, less hydronium than even something like hydrofluoric, which isn't even that good, 10 to the negative 4. Keep going down the chart, and there's tons that are in there. Keep going down the chart, name a whole bunch of them, and you get to one that is semi-familiar, maybe to you, ammonium ion. So ammonium is NH4. Again, it has a double arrow, and it's really small, 5.6 times 10 to the negative 10. Like, that's really quite teeny. Like, we're getting to the point where, like you're making barely any products. Now, you are going to make products. Like, it's not like you make none. And you'll see that from a pH perspective, it still alters the pH. It still makes it less than 7. It's still an acid. It's still going to make it. But it's further down on the chart because it's weaker, and you get progressively weaker. You get down to the very bottom, and you have this acid called ammonia. And you might say, well, ammonia is what? Somewhere back in lecture number, I believe it was 1, we were talking about ammonia, and it was a base, right? It's the active ingredient in glass cleaner and Windex. And it's a base, so why is it even on the acid side? Good question. So why is it on the acid side? Well, it has H's. I mean, it could donate an H to another molecule, but you will notice that the arrow that's on the chart, and the one that I've drawn here on the board, is going the opposite direction. Like it's not even going left to right, it's going right to left. 100% right to left, one arrow. What does that mean? That means that whatever is over on the product side goes back to the left-hand side 100%, which means what percent goes left to right? 0. So ammonia, you put ammonia into water, it does not act as an acid. It goes 0% donating H's to water molecules. So never think ammonia is an acid. Ammonium is, ammonia isn't. So hopefully that you start to get the sense of, okay, so if you're really good going left to right, okay, so perchloric, really good going left to right, 100% left to right, 0% right to left. So if you're really good as an acid going left to right, the base that's over on the right-hand side sucks going back to the left. As you go down and down and down and down, if you suck as an acid, like 0%, that means the thing going in the opposite direction is really good, 100%. And so the opposite directions have to do with each other. So you can see that if you, as you get weaker as an acid, your conjugate base, the thing on the other side, gets stronger. And the two are connected to each other because it's whether you can get rid of an H or pick up an H. That's what it comes down to. So kind of understanding the principles behind the table, it's really helpful to actually understand the organization and what it means, and positionally, what does it mean? We'll get into that way more later, but I want to talk about a couple other things here on the table. So the other thing that's on the table, and it's typical of these tables that you'll see in a data booklet or you'll see online or something like that, they tend not, it's kind of funny because they put on the one for the provincial exam, they said relative strengths of Bronsted-Lowry. I didn't put it up here on my table, I didn't have room, but the actual table itself says relative strengths of Bronsted-Lowry acids. And yet they wrote equations of them acting as Arrhenius acids. Arrhenius was dissociates to produce H plus in the anion. Bronsted-Lowry donates an H to water to produce hydronium and its conjugate base. So these equations themselves aren't really what I've been talking about the whole time. So you have to understand that these acids are unloading an H, but the H isn't floating around on its own. It's actually being donated to something. This is a shortened version of all of those equations. So really what you should be able to do in your own mind is say, okay, so really over here, it's all of these acids plus water. And then over here, instead of H plus, it says hydronium, H3O plus. Okay, so that's the equation I'm going to use, even though the data booklet I'm using has them in this form, just so you're not totally confused. Okay, so now at this point, I want to take a weak acid and I want to say, okay, we're going to make a solution out of this weak acid. What is the hydronium and the pH that results from this weak acid? Okay, so here we go. I'm going to leave that up just for a sec. Okay, so I guess I'll frame it by like putting up a question, and then we'll walk through that question. I'll show you all of the kind of the ins and the outs. Next class, I will go through okay, so what if this doesn't work, or we ask the question a different way, or ask a different thing, or we ask you to go in the reverse direction, or like all of the kind of the little weird little intricate changes you could make to come up with different scenarios and different calculations and what would you do in a lab and all that kind of stuff as well. But I'm going to walk through this one just to give you a sense of, okay, so here's the basic part of it all, and we'll get to the complex ones next class. Okay, so I'm going to write a question up here and we'll kind of frame the rest of the class on that. So here's the question. What is the pH of 0.6 molar acetic acid at 25 degrees Celsius? Okay, so first thing I wrote that at 25 degrees Celsius there at the end, for a couple of reasons. One, to remind you that we're trying to deal with 25 degrees Celsius all the time. And this is why, like we're actually in this section, we're talking about this table. And this table, if you've got one sitting there in front of you, and if it's a good table, and if it actually has kind of the details to it, it'll say, and this one actually says underneath, it says at 25 degrees Celsius. Equilibrium constants are temperature dependent. So Ka's, being equilibrium constants, are temperature dependent. So if you have an acid and it's water and it's not at 25 degrees Celsius, then the numbers that are on this table cannot be used. You have to use one that's temperature specific. Or you have to find a way, which you will in first year university and beyond, there's a way to figure out what the new value of the equilibrium constant would be given a different temperature. Okay, so that's way more thermodynamics than we're going to do in Chem 12, but it's interesting as you figure it out later on. So 25 degrees is really important, so we can use our table. Now, the question is saying, it doesn't give you a whole heck of a lot. It tells you it's acetic acid, and it tells you it's 0.6 molar. So it's telling you, and recall from last class, it's telling you what the concentration of the stuff was when we made the solution. So, like the lab tech, or where we buy it from, or me as a teacher handing it to you, or you as a student creating the solution. You know what you made. You know the volume of the solution that you made. You know how much of the solute you put in there. So if you made a 0.6 molar solution of acetic acid, you put in X amount into Y amount or Y volume of water, and you mixed it up and you fully dissolved it, and there you go. You've got this concentration. You stick a label on the bottle or the beaker and say, this is the concentration of the solution I just made. Does that mean everything is there unreacted? No, not necessarily. It might have gone, the concentration might actually be lower because that chemical has reacted in its equilibrium, but that's what we made. Okay, so keep in mind that I'm asking you a question that 0.6 molar, I could also say if you took 10 grams of solid acetic acid crystals anhydrous, and you put it into 500 milliliters of distilled water at 25 degrees, what's the pH of the solution? Well, the expectation there is that you can take a mass of a known solute, convert it to moles, divide by the volume, and get the concentration. You could come up with the number that I put into the question, or something like that. Okay, so I've kind of jumped to the chase on this one. So I've got 0.6 molar acetic acid. So acetic acid, what's acetic acid? Oh my goodness, I didn't even listen in Science 10 how you name it, how you name acids. I don't remember how to do this. Thankfully, the table has the names on it. Now, acetic would mean that it is acetic would be the acid that derives from the anion acetate. Okay, so acetic, acetate. If it was acetus, which there isn't really anything, I'm just making that up. If it's acetus, then it would have been from an anion that had one less oxygen to it. So something a little bit more like nitric is from NO3 negative, it's that acid, versus nitrous, which is from the NO2 negative ion. And hopefully that makes more sense than acetic and acetus. Anyways, so we're talking about the acid that has acetate with an H on it. You still might not know because maybe you haven't memorized what acetate is. There are always ways of figuring out what the formula of the acid is. The first one is by looking at your table. They give you the name. Now, you better know what the name is, obviously. So you look down here and you go, I don't see acetic even on here, because the word that you're going to see is ethanoic. Ethanoic acid is the new modern organic form. This acetic acid is an organic acid. So when you're doing organic chemistry or any organic chemistry you've done in the past, there's naming, there's nomenclature, there's rules, the IUPAC rules, I don't know if you remember them, that kind of decide what the name of an organic compound is going to be. So ethanoic means a 2-carbon F, single bonded ethane, and oic acid. So ethanoic acid means that it's got a carboxylic acid group and it's a 2-carbon compound and it's organic. So that's the newer name, but prior to all of that modern organic chemistry, acetic's been known for however long, since the alchemists way back in the day. So, I mean, it's just vinegar. I mean, they used to pickle things out of it. So acetic acid has been around for a very long time. So the name acetic acid is kind of the old school. That's what most people use. And ethanoic is more modern. And you'll see that a few times, and you have to know that about the organic name versus the kind of the old school common name that people use. So ethanoic and acetic is one of those. Okay. Having formic and methanoic is another one that you're going to see on this table as well. So acetic acid. So acetic acid is, according to the table, it's CH3COOH. Okay, it's one of those COO acids because it's an organic one. So I'm going to write it down. Okay, so let's kind of go back in time. We made the acetic acid solution. So we took some crystals of acetic acid. We dissolved them into water. First thing they did is they formed a molecular solution. So that's why I've got CH3COOH in aqueous form before it does anything. Then it bumps into water molecules. And they are in liquid form. They then, because it's a weak acid, form an equilibrium with hydronium and CH3COO- acetate ions. And acetate is the conjugate base of CH3COOH. Now, this thing forms an equilibrium. So the original compound was acetic acid. We put it into water and it formed hydronium and the CH3COO-. Now CH3COO-, you go, well, hey, wait a minute, the chart says that thing's a base. Well, yes, in this equilibrium, it'll pick an H up off of the hydronium and go back over to the other side. It's participating in this equilibrium. This equilibrium has a product of hydronium. So yeah, you can kind of get caught in this endless loop of this thing goes over here, blah, blah, blah. But the idea is this equilibrium is producing hydronium above and beyond what was in the water previously. Okay, so it's the hydronium that we really care about in here. Now, how do we get the hydronium concentration? This is the equilibrium. And based on what's over here, we're going to be using this equilibrium as our source of information for, one, the K expression, and two, building the IRE table. Okay, so this is a weak acid. Anytime you have a weak acid, you're weak anything, it's going to form an equilibrium. And to figure out an equilibrium calculation, or to do an equilibrium calculation, sorry, you need an IRE table. ICE, for those of you who are in the ICE camp. Okay, so I'm going to draw one. So I'm just going to do the I, the R, and the E. Okay, now you draw the IRE as neatly as you possibly can. obviously. Try not to make it super scribbly. And you put in what you know. And you know quite a bit. Okay, so you know, first thing you know is that water is in a liquid form. It's not going to change concentration. Anything that's in liquid form and doesn't change concentration is not going to be part of the equilibrium calculation. So I'm going to cross it out. It's not that it doesn't participate in the reaction. Yes, it's a reactant. It's not changing in concentration, so it doesn't have an effect on the equilibrium constant. So I cross it out. What else do I know? I know the initial concentration of the acetic acid. It was told to me in the question. So 0.6 molar. You can put the molar in if you want. I'm not super picky about putting molar in because I understand that an IRE table is really just, it's a graphic organizer for organizing your numbers and your thoughts. So it's not really an official communication thing. It's just you just kind of figuring something out. But that might be different for other teachers. They'll tell you what they require and what they don't require. The other thing that I know initially is that these two concentrations, because it hasn't happened yet, the whole idea of initial means that the reaction hasn't happened yet. We haven't got any collisions between water and the acetic acid, so we don't have any of those things. Again, I think I said this last class, that this number that's over here for the hydronium, we say it's 0 because what we're saying is the amount of hydronium that's in the distilled water. Imagine beaker of distilled water, you haven't even added the acetic acid crystals in it yet. The distilled water is at equilibrium, and it's got 10 to the negative 7 molar hydronium, 10 to the negative 7 molar hydroxide as well. So it's sitting there neutral. There is some hydronium. It's not technically 0. For all intents and purposes, it is 0. That is such a small number compared to what is going to be produced. So to make life easier on our mathematics here, we're going to make the assumption that the hydronium starts at 0. It's insignificant relative to how much is going to get produced. Now, next class, or it might even be one more, we'll kind of see how long it takes us to get there. There can be times where that assumption doesn't actually quite work. So we'll deal with that when we get there. 99% of the time the assumption works. So we've got those initial values. Do we have any indication of what we have at equilibrium? And the question says nothing about equilibrium. It tells you you've got the initial acetic acid, and that's it. That's really all it is. So far the IRE table has been, we have the initial numbers, and we have the IRE table, and that's based on our understanding of what weak acids do when you dump them into water. What else do we know? We know it's going to go, right? Like if you have 0, how can you form an equilibrium if you've got 0 concentrations of something? You can't form an equilibrium. You can't have zeros kind of going down onto the equilibrium line because you can't do math then. It doesn't form a constant. It's just 0. So we need numbers over there. We know for a fact that during the reaction, like on the R line, it is going to proceed towards those zeros. These guys are going to go up. And the other guy on this side is going to go down. We know that for absolute certain. What we don't know is how much. There's no indication. We don't know. We're not given a value about equilibrium, so we can't compare the zeros to something or the 0.6 to something to see how much it went up or down. So we know it goes, we just don't know how much. And when we don't know how much it goes, we have to assign a variable to it. The interesting thing is we're not doing systems of 2 variables here in Chem 12. We use 1 variable and 1 variable only. So everything has to be in terms of the other, of 1 variable. Well, the good thing about chemistry is everything follows stoichiometric ratios. So if 1 goes down X amount, everything in that chemical reaction is either going to go up or down relative to that amount, and that's based on what the coefficients are. Acid-base equilibria are super easy from a stoichiometry point of view because everything's 1 to 1 to 1 to 1. So whatever you label as your variable, that's going to be the same thing for everything. So if the concentration of the acetic acid goes down X, Well, this guy goes up x. And this guy, whoops. That guy goes up x. X, and x. Super easy. Okay, then obviously you can fill out what's on the equilibrium line. Now there's going to be variables there, but that's okay. We have something on the equilibrium line, which is good. So we have 0.6 minus x, and then we have x and x. X being kind of a critical value here, if you can kind of foresee the future here on the algebra, that when you solve for x, x is going to be the hydronium, which is the critical value. I mean, it's also this. It also tells you what the acetic acid finished at, but the question didn't care about those two things. It cares about the hydronium because it asks you for pH, and all pH cares about is hydronium. So the x being the hydronium, that's a good thing. So once we solve for x, we're good. So we need the algebra now, and obviously to solve for something you need an equation to solve for it, and that's where the k expression comes in. So the k expression for this guy, and yes, you need the formula, you need to write it down. You can't just jump in and just write it all down. You have to prove and communicate to the person that is reading this stuff that you understand what formula you're supposed to be using. This isn't just a fluke. So you know that the Ka of this equilibrium equals, and you're going to use the actual, you're not going to use the generic version, you're going to use the actual equilibrium that's there. So I've got hydronium times the acetate over the acetic acid. Now, if you want, you can write little subscripts of EQ to remind you that you're talking about the equilibrium concentrations of these things. Later on, we might be doing, working in backwards and what was the initial concentration, like all that kind of stuff. So you might want to get in the habit of writing little EQs for equilibrium and I's for initial, maybe even a subscript C for a change if you want, whatever. I don't require it, so it's up to you. It's up to your teacher. Now, we've got the K expression, which is our little formula. Now we plug in what we know. So what do we know? Well, we know it's acetic acid, and we know it's at 25 degrees. So we have a table that tells us what that Ka value is. And so this is the left side of this equation. The Ka is an actual number, and that number we can put in. So I'm going to put in what acetic acid's Ka is. 1.8 times 10 to the negative 5. That's its Ka equals. Okay, now we're talking about the E line, right? Like we don't want the I line, we don't want the R line or the C line. We want the E line. Equilibrium is what the K expression uses. So we want this line here, right? We want that guy down there. So it's going to be the hydronium times the CH3COO minus. Each of them are x. So I'm going to kind of cut to that mathematical chase. X times x is going to be x squared. Over the acetic acid at equilibrium is 0.6 minus x. Okay, so there is our equation. Now, I'm going to erase this over here because I need space. I might even start writing a little bit smaller because I'm going to run out of space if I don't. So here's our little formula now down here. Not our formula, it's our equation, sorry. And for those of you who, not for those of you, all of you have the math to know that this is a degree 2 polynomial. It has an x squared in it. As an x squared, it has an x, which means that this is going to be quadratic. So, yeah, you could, and the reason why I'm not doing it is because you don't have to. I'll show you how. You could, if you wanted to, multiply all of this thing out, move all the terms onto one side, put it into the formula of ax squared plus bx plus c equals 0. put it into that form of a quadratic equation. Take your A, your B, and your C and put it into the quadratic equation, okay, or the quadratic formula. And if you put it into the quadratic formula, you'll get two answers, right? Because you always get two answers as a degree 2 polynomial. You get two answers. One of them will always work and one of them won't work. And like literally it will, by work, I mean, you'll put it back into the IRE table and you'll actually get numbers down here. Or you'll put it in and like this will be a negative number or something. Like one of the answers will be 0.8, and so 0.6 minus 0.8 will come out to negative 0.2. Well, that's an impossibility in chemistry. You can't go below zero things. So you can do that. And if you're really comfortable with math and you know the quadratic formula, or you've got the thing stored in your graphing calculator and you can just punch in A, B, and C and hit enter and it kind of pops out the two answers, then go for it. Right? If you know you're not going to make a sign mistake, or like in the algebra of moving everything onto one side and all that, it works. Every single time it always works. No issues with it at all. Interestingly enough, the BC curriculum has always said in the past, you don't need to be able to do that. You don't need to be able to do the quadratic formula in order to solve these things. Well, you might look at it and go, well, how is that even remotely possible? Because it's got a squared in it. You have to do that, don't you? No, you get to use a little bit of chemistry, kind of interesting little maneuvers here. These maneuvers don't work in math class, and I'm about to show you, but they work here in chem class, and it's based on some theory. So here's the theory. So the theory is, I'm going to take my little equation right here, and I'm going to rewrite it up here. 1.8 times 10 to the negative 5 equals x squared over 0.6 minus x. Here's what we do in chemistry and chemistry only. We look at the bottom of the fraction, and really, to be honest with you, the problem is this thing. It's actually that x. It's when the subtracting the x from the 0.6 that mathematically is the problem. Because if you had x squared equaled some number, you just take the square root and you'd be happy, right? But that x kind of throws you for a loop. You can't take the square root of both sides when there's an x to the power of 1. So here's what we do. We drop the x. Like we literally eliminated the single x. Not the squared one, but the single x that's there. And you might go, well, you're not allowed to do that. That's not math. You can't just drop a variable and come up with a right answer. Well, you kind of can in chemistry when whatever that value is going to be is insignificant relative to what you're subtracting it from. So if x was really, 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 really teeny, okay, and I'm going to make up a hypothetical here. Let's pretend, it's not going to be, but let's pretend. Let's pretend x came out to 0.00007. 0.00007. 0.6 minus 0.0007. So this is hypothetical here. This is not the answer. So if x came out to 0.00007, you would be subtracting it from 0.6. And if you subtracted it from 0.6, you would get 0.59993. Correct? I mean, you pull out a calculator and check my math if you want, but I think that's correct. But in chemistry, we talk about sig figs all the time, and levels of precision and all that kind of interesting stuff. Well, this 0.6 right here was actually the measured quantity. It went to the 10th of a molarity. Well, the 0.00007 is way more precise than 0.6. And so when you subtract it, does it actually change the value from 0.6 to 0.59993 when you don't even know that the 0.6 was really that precise? No, you don't, because the 6 didn't have a bunch of zeros after it, which means it wasn't measured terribly precise, which means that who says your answer can be that precise? And that's exactly what sig figs are all about. So if you're doing this and you're using the subtraction rule, the subtraction rule in the use of sig figs, the subtraction rule says you can only be as precise as the least precise place value, not least precise number of sig figs. Subtraction and addition is place value. So the least precise place value is a tenth in this because of the 0.6. The other guy goes to too many places. So that means you have to round it to the nearest tenth. Well, if you round this to the nearest tenth, what do you get? It comes back to 0.6, which means that the answer of 0.00007 was insignificant relative to the 0.6, so who cares if you got that value anyways? You were just doing math that essentially used 0.6. Well, if you're doing math that essentially used 0.6, why even have the x in the first place? Like, remove the x. Get rid of it. And so we're using our sig figs to our advantage here. We're saying that whatever is produced over here, okay, so this value of x, acetic acid, weak acid, all the weak acids are pretty weak. They don't make very much product. Because they don't make very much product, that value of x, whatever it's going to be, we're going to make the assumption it's going to be really, really small relative to that amount of acetic acid that it began with, the 0.6. And when we're making that assumption, we're saying, well, it's not even going to change it mathematically, so let's just keep it where it is. Now, we don't just erase it like I just did. What we actually do is we indicate to the reader that we're making that mathematical assumption. So over on the side, you write assume, you write the actual assumption, assume x is going to be significantly smaller than 0.6. X is going to be smaller relative to the number you're subtracting it from. And that's kind of the critical thing. You have to focus in on, okay, so this is what we're assuming. It's small relative to this value that we're subtracting it from. Therefore, in this one little bit of the calculation, not all over the place, in this one little bit of the calculation, the value of x will not have an effect on the overall answer. And so, because you're stating that, now you can write the line and now you got rid of the x to the power of 1. Now I can multiply by 0.6, take the square root, get an answer. So, making this assumption, if you know you can do it, well, it's way faster than doing the quadratic. Right? Way faster. Now, remember earlier I said 99% of the time it works. Well, what happens is in the 1% of the time where the assumption doesn't work? And I'm going to show you that when we're done this question. Kind of how you check to see if your assumption actually worked. Next class, I'm going to show you, well, if your assumption doesn't work, what do you do as a result of it? But for now, we're going to carry on with our math. From now, it's fairly straightforward. So now, I grab my calculator, and I go, so x squared, 1.8 times 10 to the negative 5 times 0.6, right? So I'm multiplying by 0.6. So 0.6 times 0.8. Okay, we had a little bit of a glitch there. My computer kind of glitched out, and then my calculator glitched out. So back to this calculation. So we've got the Ka of acetic acid, which is 1.8 times 10 to the negative 5 times 0.6. Okay, so it's sitting there on my calculator. What I'm going to do, I'll write it down. That's fine. I wouldn't normally write down that line. Simply, I'd just leave it on my calculator because I'm going to take the square root next, right? So I'm not going to round it to the number of sig figs because I'm not done the calculation yet. So I'll do that at the very end. So I will now take the square root to solve for it, right? So x equals the square root of that value. Okay, so I've still got it on my calculator, so I can just take the square root of it. And x equals 0.00328 sig figs. Okay, so how many sig figs do I get? Well, we have to kind of look back at our calculation here and try and figure out what are limiting factors here. So our calculation, when we originally plugged in these values right here, so the Ka had 1.8, so that's 2 sig figs, and the concentration down here had 0.6, so that's just 1 sig fig. So I only get 1 sig fig on my answer. So that number over there, I'm only going to take 1 sig fig. Now, the question technically said, what is the pH of? So on my calculator, I've still got the unrounded version still sitting there on my calculator. I'm going to actually leave it there. Now I might write down that the hydronium equaled 0.003 molar. I might write that down. That doesn't mean it's my final answer to the proper number of sig figs. I wouldn't erase this and then put in 0.003 and then do the negative log. I would leave the unrounded version, take the negative log, and then take the pH to 1 sig fig. So I'm going to do that right now. Okay, so I'm going to take the log of that value. I need my, sorry, different calculator. I need my glasses to see it. So I'm going to take the log, and I get 2 point, okay, so the 2, sig fig rule, the 2 does not count as a sig fig. Whatever I write next, the one after the decimal, that's my first sig fig. So it says 2.4832, blah, 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 blah. So it's either staying as a 4 or it goes up to a 5. And because there's an 8 to the right of the 4, I'm putting down 2.5. And so the pH of this solution is 2.5. And that's the answer to my question. So you can see that there's quite a bit of algebra to it. So you got to write down the chemical equation, right? You got to actually write down the equilibrium, an IRE table, fill in the IRE table, K expression, fill in the components of the K expression, make the assumption, which is kind of a critical part of doing the math. Now, of course, you can do the quadratic, and that works too, whatever you're comfortable with, but the assumption works pretty quick too. You drop the x that's being subtracted, and you carry on with the math, come up with an answer, and that's the hydronium. Now, if someone asks you, what's the acetate concentration floating around in the solution? Well, it's same thing. It's also x floating around in that solution. Now, I said that I was going to show you how do you know if your assumption worked. You should actually check your assumption. So you should come to this point right here. Okay, so where you're, that point where x equals something. And you should say to yourself, is that okay? Like, does my assumption work? Coming back up here, when I said x is going to be significantly smaller than 0.6, therefore I can drop it. Was it? Was it significantly smaller than 0.6? And could I get away with dropping it? Well, what you can do is you take your answer, whatever x came out to, and you, using your sig fig rules, you check to see when I actually subtract that actual number and I apply sig fig rules, did it stay as a 0.6 or did it change? So you kind of do over on the side what I showed you earlier with that example, where you take the numbers that you're actually using here. So 003286. So I actually take 0.6, I actually subtract the answer that I got for x, and I ask myself, using sig fig rules, did it significantly change the 0.6? Like, did it go down to 0.59? Or, well, it couldn't have, because it's only one sig fig. It would have to go down to 0.5. Did it change it down to 0.5? Yes or no? And the idea being that when you use your sig fig rules for subtraction, it's place value. So this guy would have come out to 0.596714. So that's what it came out to. But using the sig fig rule, to the right of the 5 is a 9, which means that that 5 would have had to round back up again. So the assumption is okay, because it rounded back up to a 0.6. That assumption is kind of a critical little piece here, unless you're planning on doing the quadratic all the time. And if you do the quadratic all the time, then you don't have to worry about an assumption. You just solve as if you were in math class. You got a little equation, solve using quadratic formula. So that is the basic gist of what we're going to be doing with weak acids. So you need an equilibrium, you need an IRE table, you need a K expression, and then you plug in the values and you solve for different things. You can probably already see there's a couple of different things that you can do. What if I gave you equilibrium numbers and I asked you what's the identity of the acid? Well, you could solve for a Ka and you could look on the table and say, well, it's this acid because that's what the Ka was. So there's a whole bunch of different things that we can do. What if that assumption little check that I just did there doesn't work? What do you do then? Like, well, do you just bail and, well, it didn't work. Who cares? What are all the different kind of ins and outs and different kind of tricks and things that we can try and get you hung up on as a chem teacher? So that'll be next class. So when I see you next, make sure you bring a Ka table, because you want to have a Ka table. You like to be able to see what I'm referring to and me not just kind of putting it up in front of the screen and you hope you can see it. You want to have one right in front of you. And you want to have your calculator as well, so that when I'm doing a calculation, you make sure that you know where the buttons are that you're supposed to be doing. Okay, so I will see you next time, and we'll work on those more complicated issues.